So, okay, it looks again like we started a recording. So, we had Fermat's little theorem, right? Actually, in the book, just called Fermat's theorem. And that was the thing about taking big powers and looking at a modulo of prime and all that sort of stuff. And so we have this idea that took hold a while back. And I like reading this part of the book because as you go through and read sections 16 and 17, and the author talks about it, at the time he wrote this book, and through all of my undergraduate career, and I guess all of my graduate career, Fermat's theorem was still not a theorem, it was a conjecture. So we could call it Fermat's last theorem, but Professor Dudley, who wrote the book, quite correctly says it's not a theorem, it's a conjecture. And so it really wasn't Fermat's idea, right? We've seen this a couple of times where there's something with somebody's name on it, and then it turns out they weren't the one that thought of it. And in Fermat's case, he was not only not the one who thought of it, he's not the one who proved it. Well, that happens a lot, more often than you would like to think if you're the person who put all the work into proving the thing. So Fermat's conjecture considered this, that let's see, the Diophantine equation x to the n plus y to the n equals z to the n. We've just looked at the n equals 2 case. And we've not only shown that there were some solutions, we've given a recipe for finding all of them. Right? We can take any solution that we're trying to produce, we'll produce a fundamental solution, and then we've either, the ones that are not fundamental solutions are just multiples of fundamental solutions. So the Diophantine equation x to the n plus y to the n equals z to the n has no solutions if n is bigger than or equal to 3. And that really, on the surface, is kind of shocking. Well, it has no solutions. I guess I should say non-zero solutions. So if you let one of x or y or z be 0, then the thing has infinitely many solutions. Right? So if y is 0, then just take x and z to be any two numbers, and they work. But in any of the cases that are interesting, where x, y, and z are non-zero integers, so the use of the qualifier Diophantine equation means we're only interested in integer solutions. There are no solutions in the integers, in the non-zero integers, if n is bigger than or equal to 3. And the story goes, right, that Fermat read this in a copy of a number theory book written by Diophantus in ancient Greece. And he put in the margin that he had a marvelous proof of this fact, and the margin had not enough space to write this proof. And then he went off and died, and then somebody found his copy of the book 5 decades later or something. And then people said, well, gee, Fermat was a pretty smart guy, but there are smarter people. Euler was around, Gauss was around. Some of these people are, Fermat wasn't bad, but there were certainly lots of really bright mathematicians around. And they kind of figure, well, if that guy had a proof, we ought to be able to find it. And so another 300 years goes by, and nobody comes up with a proof. And I think the correct date of the proof, it has to have been, I keep wanting to say it was 1996 when I had to come down. No, I wouldn't have flown down to Texas in 1996 because I was living in Texas in 1996. It has to be 1993. 1993 must be the year that one of my grandfathers died. The other grandfather was in the hospital getting multiple bypass surgery, and so I flew down to Texas for all sorts of really not pleasant stuff. And my aunt, I ran into in the corridor at the hospital, and she started yammering about this really famous math result that had been solved that she had seen on the evening news. And the history of Fermat's conjecture is just littered with people making claims that they had solved it. In fact, this has been a nuisance to professional mathematicians for centuries. And I think it's related in this book that one famous mathematician had postcards printed that said, to respond to people, and they were pre-printed, that said, your solution to the Fermat conjecture is in error. The first mistake lies on page such and such. And he would hand these postcards out to his graduate students and let them figure out where the error was, because he just knew there had to be an error, because an amateur is not going to come in and prove this thing. And so this guy, Andrew Wiles, was just the latest guy. There was a Japanese guy back in the 50s or something who spent his life trying to prove this result, and when he presented what he thought was a proof in a meeting and people shot it down, he was so distraught he subsequently committed suicide. I mean, mathematicians get really, really, really invested in the things that they decide to work on. And so Wiles is just this mathematician in England. He'd been working on this for about 7 years. I need to look it up. There's a wonderful NOVA episode. If it's actually available on the internet, I need to put a link to it, because I think watching him in this NOVA episode, which was produced within a year or two of when his proof came out, when this man, who's in his early 40s at the time, is talking about this problem, he talks about being first exposed to it when he was in essentially junior high school, which is where I remember seeing it, in the margin of a book, oddly enough. It was an interesting footnote, probably right next to a discussion of the Pythagorean Theorem. And Wiles, when he's talking about this, just gets almost giddy. You can see this, little boy, 13, 14-year-old excitement that he decided when he was a teenager, well, that doesn't look too hard, I'll try to prove it. Because it doesn't look too hard, right? It's just whole numbers. And so then he goes on and becomes a professional mathematician and takes a huge career risk, because he basically spent all of his time at home in an attic office working on this problem. You don't dare tell people professionally that you're working on this problem, because it has befuddled the most brilliant mathematical minds of 3.5 centuries, right? It was something that Gauss couldn't do, Euler couldn't do. All the big names you've heard of, any of them 19th century mathematicians who were starting to get really sophisticated. Probably any mathematician of any repute has put some thought into this problem, and some of them invested a lot of effort, and in some cases they've invented whole new areas of mathematics, in abstract algebra, and in number theory, and in topology. Because you see, you can look at this equation, and you could think of it geometrically. It's a problem in R3, three-dimensional space. You've got a surface in three-dimensional space where x to the n plus y to the n minus z to the n equals 0. This is what's called the level surface of a three-variable function. And you might have talked about those in Calculus 3 when you were looking at Green's theorem and Stokes' theorem and some of these things, doing integrals over surfaces in three-dimensional space. And so if you think about, just imagine this being some kind of surface. We don't have to worry about what its shape looks like. That's for topologists, and I'm not one. But you're just trying to find integer lattice points, right? The integer lattice in Rn just looks like a big cage kind of thing, like a salt crystal kind of. And you're just trying to find any points that are corner points in that lattice that lie on here. In 2 dimensions, when you talk about x to the n plus y to the n equals z to the n, if you take a particular value of z, if you think of this in 2 dimensions, once you fix z, well, if n is equal to 2, x squared plus y squared equals r squared, you're looking at a circle. And you're asking, where does that circle hit integer lattice points? And some circles do, and some circles don't. So it becomes a little more complicated. The surfaces are harder to think about, but you can think of this as a problem in the plane or in three-dimensional space. And so you can at least get a qualitative sense of how this could lead into a geometric approach to it, or an area of math called algebraic geometry that kind of combines all these ideas and mixes in some topology. And so those large chunks of those areas of math were developed to try to solve this. There's a branch of mathematics called ring theory and abstract algebra. And a lot of the key ideas in 19th century ring theory essentially came out of trying to look at this equation. We've already seen that you can get some mileage by looking at the integers mod n. Well, the integers modulo n for any n form a commutative ring with a 1, something called a commutative ring with unity. In some cases, when the modulus is prime, you get something called a field, which has essentially all the nice properties that the real numbers have. You don't have zero divisors, right? Anytime two numbers multiply to give you 0, one of them had to be 0. Every non-zero number has an inverse in a field. And so these ideas in ring theory, a lot of the stuff that's taught in a modern graduate level ring theory course arose originally by trying to solve this problem. The cool thing about it is nobody really cares about this problem other than Fermat wrote in a book that he had a clever solution, and so they thought, well, let's see if I'm as smart as this guy. I would love to see somebody come out and actually produce a proof that Fermat could reasonably have had. Because Andrew Wiles's proof uses algebraic geometry, it uses topology, it uses all sorts of abstract algebra that did not exist in Fermat's time. It had not, was still centuries away from being invented. And so there is not a proof in the sense that there's a nice number theory proof of the sort of thing we just did. And so you could win a Fields Medal by, which is kind of the highest prize you can get in mathematics, by coming up with a proof within the context of number theory as people in Fermat's time would have known it, mathematicians at that time would have known it. Wiles's proof is probably only understandable by a very small number of people on the planet. I mean, it uses so much complicated math that there probably can't be more than a couple hundred people, or maybe only a few dozen people on Earth who are capable of reading and understanding that proof in its entirety. So it is really, really complicated. When they found a hole in his proof, as they had in all the other proofs, he was able to patch it by getting together with a colleague. He had taken a shortcut, and he had to go through and do the hard work, and so I think that's like a 100-page appendix to the original proof. Anyway, it's been kind of a wild story. It is now a theorem, but it properly ought to be called Wiles's theorem, except that Wiles would be the first to tell you that his work was built on the previous efforts of probably dozens, if not hundreds, of mathematicians. So looking at this thing, you might think the next natural thing to do would be to look at the n equals 3 case. And we could do that. That case gets a little bit hairy and probably is beyond the scope of what we're able to do. But I want to look at, so where we're going with this is we'll get to the n equals 4 case. And so we'll be looking at x to the 4th plus y to the 4th equals z to the 4th. Now, what we can really do is, that's actually not what we're going to look at. We're going to look at a related Diophantine equation. Really, we're going to look at x to the 4th plus y to the 4th equals something squared. Because if this thing has a solution, right, then, well, basically, because I can view z to the 4th as the square of something, if I can show that this second equation has no integer solutions, no non-zero integer solutions, that will imply that the Fermat equation in the 4 case has no non-integer solutions. So our strategy is going to be to look at this, but in fact, you could really hope that you would find actual solutions to this, because of course, x squared squared plus y squared squared equals z squared squared. If I just ignore that the things in the, basically I'm looking for Pythagorean triples consisting of 3 perfect squares. If I think of this as being my A, this as being my B, and this as being my C, then the 4 case, well, this doesn't seem outlandish, right? Okay, I know how to find all Pythagorean triples. I just now need to hunt among them and find some where all three numbers are perfect squares. Unfortunately, it'll turn out that that answer comes up in the negative, that there aren't any Pythagorean triples where A, B, and C are all perfect squares. And that's going to then imply that we can't solve this. So that's kind of the direction we're going to go with that. We're not going to go in that direction right now. Let me just tell her real quick. My daughter. So that way, if it's urgent, she'll know to call her mother. So anyway, I hate to stop class for that, but every now and then, if she calls again, I'll answer it, because they know that if they call twice, it probably means something is really important going on. So what we're going to do right now is just kind of flesh out this idea of Pythagorean triples. So just to summarize everything we've done so far, we know that a squared plus b squared equals c squared, with a, b, and c all greater than 0, and a and b relatively prime. That's now if and only if you can write a equals 2 times m times n, b equals m squared minus n squared, and c equals m squared plus n squared, with m and n relatively prime, and m greater than n greater than 0, and m and n not congruent mod 2. In other words, one is even and one is odd. So we know how to produce all primitive Pythagorean triples, and that will be useful to keep in mind. So among the problems that I picked out as being potentially interesting, and I got to cheat a little bit and just look at the book, because I want to make sure that I leave some that I don't do. So the first one I want to look at is has to do with fundamental Pythagorean triples, which is number 3. Find a fundamental Pythagorean triple with a leg of 100. So so this problem, find a fundamental Pythagorean triple with a leg of 100, not 110. So you have written above the sum total of everything we know about primitive Pythagorean triples, or fundamental Pythagorean triples. We want one with a leg of 100. Where can we start? And you don't have to pop an answer right out. Let me give you some think time on that. And of course, you can play along at home. Oh, it looks like we are down 1 online. As far as I can tell, though, we are still broadcasting, right? So I guess for Shauna and Meredith, are we still audible? Oh, good.
Yes.
Good. I just noticed that Lauren either got kicked off or has wound up having to leave us. So I just wanted to check. So knowing what we know about fundamental Pythagorean triples, where can we start with this? Or can you actually tell me what an answer to it would be?
I first started just like subtracting one, but I did not want to do the whole math and to see if that was one of them, you know. But then I put A as 100.
Okay.
And I know now that either M or N has to be 50 divided by whatever M or N.
Okay, so a reasonable place to start would be to say, well, we already know that one of the numbers is even, and the way we've got it set up, A is going to be the one that's even. So the even one, the even leg would have to be 100 because 100 is an even number. So you could look at the idea that A, which is 2mn, would have to be 100. And so m times n would have to be 50. You also know that m and n are relatively prime, and that one's even and one's odd. So what might we do from here? So we can use the fact that we can factor this as 5 squared times 2. And so for 25 to split up as a product, or 50 to split up as a product of two things that are relatively prime, it has to be 25 times 2. And so we want m to be the larger of the two, so we can take m equals 25 and n equals 2. And so what that would suggest is that B would be 25 squared minus 2 squared, which is 621, and that C would be 25 squared plus 2 squared, which is 629. And so our triple is 100 and 621 and 629. And those three numbers are pairwise relatively prime. If you square the first two and add them together, and of course, I'll tell you, I did this morning. I worked out this problem and I thought, okay, I got to make sure that this works because I know a few Pythagorean triples. I might know a couple more than two, but not a whole lot more because I haven't had a great reason to memorize them. I did tell my students on the 8th grade STAR test that most of the problems they run into will be some multiple of either 3, 4, 5, or 5, 12. Or it doesn't work the way I'm getting better at that though. Close that. So if we take 100 and we square it plus 621 and we square it and we get that answer, oh gosh, that's pretty big. And then if we ask what's the square root of that answer, we get 629. So we actually produced a Pythagorean triple. And it's a big one, right? Well, okay, not really big, not super impressive big, but considering that all we had was one of the legs had to be 100, we've also pretty much gotten that that's the only Pythagorean triple, primitive or fundamental Pythagorean triple with 100. So this is a lot more interesting than saying 3, 4, 5. Oh, that would be 60 and 80 and 100. Okay. That all of a sudden just doesn't seem nearly as amazing as it maybe once did. So there's at least one other triple that would work, and probably more than one. But as far as fundamental triples, this is it. Oh wait, 3, 4, 5 doesn't work. I'd have to take 5, 12, and 13, right? Because I don't want the hypotenuse to be 100. I want one of the legs to be 100. Oh, so I could take 3, 4, 5 and multiply everything by 25. So I have 75 and 100, and then 5 times 25, which is 125. Okay, so I could produce that one with a leg of 100. I could take 5, 12, 13, multiply that by 20, and get another one with a leg of 100. But this isn't either one of those. So that's an example of how we could use this newfound bit of knowledge. Let's see. How about this one? This one kind of intrigued me, and there's a couple of later problems that are of this flavor. This is number 8. So, again, section 16, number 8. The problem reads that back around 1150, a mathematician, Bhaskara, who I want to say Bhaskara, I first thought was Indian, but no, he's not Indian. I think he's probably Arabic. But I could be wrong. I never took history of math, after all. Found a right triangle whose area is numerically equal to the length of its hypotenuse. Show that this can't happen if the triangle has all integer sides. So, show that area numerically equal to hypotenuse in a right triangle. It cannot happen with integer sides. So where do we even start with something like that? Okay, so if you think about a picture, and as I'm watching Sarai do this, she's looking up and kind of a little off to one side, which is what people do when they're trying to visualize something. What side were you looking off to? I don't remember what I was told that people do. Like, you tend to look off to the right or the left?
Well, I was looking to, I guess, up and right.
Up and to the right. That's characteristic of how people tend to, what they tend to do when they're trying to picture something in their mind. Trying to develop probably this picture, that if you had a side length A and a side length B and a hypotenuse of C, then with that, because you're thinking, well, what's the area of a right triangle? And so you get that 1/2 times A times B would have to equal C. Now, we've got to be a little careful here, because it doesn't say in the problem if it has integer sides that are relatively prime. So we might have to consider sort of two cases. What happens, is it possible, or can we somehow reduce the case of having a GCD other than 1 to the case of being relatively prime? And the reason that's a little bit of a problem is, suppose that A equals some D times X, B equals D times Y, and C equals D times Z. Okay? Then what you would have is 1/2 times D squared times the two legs of a fundamental Pythagorean triple would equal D times c. And the problem here is that that d doesn't show up as a square on the right-hand side. So you could say, well, that would be equivalent to saying that 1/2 times d times the product of two fundamental triple legs equals, I'm sorry, that shouldn't be an x, or that shouldn't be a c. That should be a z. And that shouldn't be a c over there then. It should be a z. So you'd be looking at a triangle with side lengths x, y, and z that are relatively prime, but now you've got this scale factor in there that's kind of irritating. So we may or may not be able to use our characterization of fundamental Pythagorean triples. Now let me look at what I wrote down and see if I had to use that in any way. Maybe not. Okay, so at any rate, the condition we're looking at, first of all, is that you've got this condition on the two legs and the hypotenuse, the thing that I've got circled right here. And we're looking at a right triangle. And we want the side lengths to be integers. So the thing I've got circled there doesn't at all capture the idea we're in a right triangle. So how could we capture the idea that we're in a right triangle?
We just do where n is equal to 2.
Yeah, that puts us in the special case of looking at a fundamental Pythagorean triple. If we try to use the theorem we just had, and it's unclear that we can always reduce it to the question, we want integer sides, but they might be a multiple of some Pythagorean triple. We might need that scale factor to show up once on the left-hand side, but not at all on the right-hand side. So, yeah, so what makes A, B, and C the sides of a right triangle? So what does Pythagoras tell us? Right, because the Pythagorean theorem is if and only if, right? A, B, and C are the sides of a right triangle if and only if a squared plus b squared equals c squared. So what we have then is that we want this with the restriction that a squared plus b squared equals c squared. Now, because that's not a c squared right there, we have one of two choices. We can either introduce the square root in this blue equation, or we can square both sides of the purple equation. So if we square both sides of the purple equation, then that could introduce c squared anyway. So what we get is that this thing becomes, why am I starting to write the letter I? Because, of course, what I want is 1/4 times a squared b squared equals c squared. So what I have is a system of two equations with three unknowns. So if I go back to the only thing my geometry students know but don't remember from Algebra 1 about systems of equations, is that the method that works for general systems of equations most often is the method of substitution, right? You can solve both equations for one thing in terms of the others, and we have this pair of equations solved for c squared. And so if you were going to guess something to do, a reasonable something would be to set those two expressions equal to each other, and that gives you one equation with two variables. You would have to have a squared plus b squared equals 1/4 a squared times b squared. Now, in solving something like this, it really is the case that all you really can do if you don't have a flash of insight is just start pushing the symbols around and hope something falls out. So a good habit of mind is to look at that and say, I don't think I'm finished yet. Right? If I'm trying to show there can't be integer solutions here, well, there's nothing in that equation that says A and B and C can't be integers yet. So I'm not done, so I have to try something. Among the things I might try, if I'm one of my high school kids, I'm going to say, oh, fractions are icky. If I'm a number theory student, I'm going to say, oh, we said the first week of school we didn't have to work with fractions in this class, so we're going to stick to that. So we could multiply through by 4 and say, well, 4a squared plus 4b squared equals a squared times b squared. Still not done, right? I can maybe find integers that make this equation true. So I could either move everything to one side of the equation, which if we had an AB on the right, so that the stuff on the left looked like the variables on the right squared, then we'd be thinking, oh, it would make sense. It looked kind of like a quadratic polynomial in two variables. We could move everything to both one side and try to factor it or something. But unfortunately, we've got a fourth power term on the right, and a squared times a b squared, so we've got a lot going on there, and only squares here. It doesn't look that much like a quadratic equation. But you could go that route and see what you could do. You could also use an idea of factoring by grouping and say, well, I could look at this and say I've got a b squared term here and something with b squared here. Let me move all the b squared stuff to one side and pull out a common factor and divide or something like that. So again, what you do in practice is you've got scratch paper and you just start fiddling with stuff and hopefully something falls out. I've thought a little bit ahead of time about this, so not very far ahead of time. But I think I remember getting some mileage. Notice, for those not physically in the room, I'm not really looking at my notes very closely. Because I'm trying to go back and think, okay, how do you think your way through this? So if I move the b squared term over the right-hand side, I could also move the a squared term over. But what I get is that 4 times a squared is equal to a squared b squared minus 4b squared. So 4 times a squared looks like a squared minus 4 times b squared. Now I am going to look over and see if I wrote down anything useful here, or if I even did this at all. Wow, this was all so clear, and I have to actually look at it. Am I making it too complicated? So what I'm looking at here looks complicated. Let's just follow it out anyway and see what happens. So the left-hand side is the square of 2a, and the right-hand side is, well, just what it is, b squared times a squared minus 4. And I think I overheard somebody say something about taking the square root. So if we did that, if we tried to take a square root of both sides, so let's think of that. Okay, then that, I did that here, okay? Whether it's a good idea or not, okay, you might hesitate on it because square roots, when you've got integers, often don't turn out to be integers. So this ought to make you, at least we're trying to show there's no solution with integers. This would be kind of a hopeful thing maybe to take a square root. So if we do that, on the left-hand side we get 2a, because everything in sight's a positive integer, the a and the b and the c anyway. On the right, we get b times the square root of a squared minus 4. see. I have a line here where I wrote without loss of generality, and now I'm not completely convinced that that has to be true. If the sides are integers, I said without loss of generality, I could take A and B to have a greatest common divisor of 1. I'm not convinced that's true. So we've got this much.
How did we go from y squared to 2 squared?
This is 4 times the square of A, and this says take 2a and square it, which would give me 4 times a squared. Yeah, it's the parentheses there that are kind of the difference. So what do we know about a squared minus 4? It's got to be a perfect square. It's the argument that I have written down here. I'm really worried about this idea of saying I could assume A and B are relatively prime to each other, because we don't know, and I'm pretty convinced we can't assume that we've got a fundamental Pythagorean triple. So A is equal. I want to think about odd prime divisors of A and B. And then I have to worry about what about things that are not odd prime divisors. So what happens if we the other thing we could look at is the square root in here. How many squares differ by 4? Because we need a squared minus, that might actually be the key. We need a squared minus 4 to be a perfect square. Otherwise, the left-hand side's an integer and the right-hand side's not. So let's think about what the squares look like. So if you start listing the squares, how often do you find two perfect squares that are 4 apart? A perfect square, or when you subtract 4, you get another perfect square. So let's just list the perfect squares. We have 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And you may or may not know this about the perfect squares. This I first ran into, and I hadn't ever seen it. I was out of graduate school. I don't remember consciously recognizing this fact until I was teaching elementary ed mathematics for the first time. Or maybe it was a math journal where I saw a proof without words of this fact. I've seen it in a couple of different places. That here you have 1, the first odd number, and then 4 is 1 plus 3. And 9 is 1 plus 3 plus 5, and 16 is 1 plus 3 plus 5 plus 7, that consecutive perfect squares differ by an odd number. And the proof without words looks like this. Here's the first perfect square. Think of it with like centimeter cubes or something. If I add another row and column, to get the next perfect square, I've added 3. And then if I add the next row and the next column, and then I have to put this in here, so I get the existing piece and then one more, I get the next odd number. So what I'm doing each time is I'm adding matching pieces they go in pairs, that gives me an even number, plus 1 is the next odd number. So the idea that perfect squares are this turns out to be really, really useful here, because you see the gap between 1 and 4 is 3, and the gap between 4 and 9 is 5, and the gap between two perfect squares is in fact never equal to 4. It's always equal to an odd number. And so you can't have but no two squares differ by 4. So a squared minus 4 is not a perfect square. Which is not how I had finished the problem, but I suddenly realized that what I had written down this morning doesn't actually work, so we might as well throw it out. And then this is just improvising a solution in a pinch, right? But it does come down to the whole reason when whoever said you should take a square root, that's actually a pretty good plan here, because that's a good place to have something come out that can't be a whole number. So now you get this number is in fact going to be irrational. It's not just not a whole number. It's not even a rational number. And so this side, on the other hand, is an integer. And if you take an integer multiple of any irrational number, you get an irrational number. And so we're done because this is a contradiction. And so we can't have A, B, and C all integers. So Bhaskara found a right triangle where the length of the hypotenuse was numerically equivalent to the area, but that right triangle doesn't have integer sides. Now we could go through and try to find his triangle, but this is a number theory class. If it doesn't have integer sides, we're not interested in it. So you want to talk about non-integer things, go do analysis. Or some other nasty, icky course like that. Let me see. There might be one more in here just for a highlight. Yeah, this one I liked because I had no idea how to do it to begin with. So this one is actually number 10. So in the previous one, we couldn't reduce it to that theorem that we have. We couldn't reduce it to the case of a fundamental Pythagorean triple. In this one, I think we can. So this one says to show that 12 divides the product of the legs of any Pythagorean triple or Pythagorean triangle. I didn't actually define the term Pythagorean triangle, but I think in the text he defines the term to mean a triangle with integer sides. So it's a right triangle, but more importantly, the sides are all going to be integers. So if we look at this one, if we have three numbers that, well, if we can show this for fundamental Pythagorean triples, then, so a strategy here is prove for fundamental Pythagorean triples, and then if A times B by 12, and if we take a triple that looks like so fundamental Pythagorean triple ABC. I should have written that down. If A times B is divisible by 12, then any multiple you get, if we take Ka, K times B, K times C, 12 will divide the product K times A times K times B, because it's already dividing the product of A times B. So in this case, if we can show it's true for fundamental Pythagorean triples, then it's going to be true for all Pythagorean triples. And so ABC is a fundamental Pythagorean triple, then what we know is that we can write A equals 2 times m times n, and B is m squared minus n squared, and C is m squared plus n squared, and we know that m is greater than n is greater than 0, and we know that m and n are relatively prime, and we know that one of them is odd and one of them is even. So that's what we have to work with. I should have had the sense to scratch out some stuff here, because I suspect a lot of what I've written down here didn't lead anywhere. And then I came up with an answer. So let's see. And there's also the time crunch of wanting to finish this up fairly quickly. Okay, so the first observation is that 4 divides A. Since one of m and n is even, and A is 2 times m times n. So 2 times an even number times an odd number is divisible by 4. So if 3 divides A, we're done. Because 3 times 4 divides A, and so it divides 8. So that would make 3 times 4 divide 8 times B, because we don't even need the B. So suppose 3 doesn't divide A. If 3 doesn't divide A, then 3 doesn't divide M, and 3 doesn't divide N. So now I want to look at B. So if we have two numbers, neither one of which are divisible by 3, then M and N are each either 1 or 2, which is congruent to minus 1 mod 3. In both cases, m squared is congruent to n squared is congruent to positive 1 mod 3. Now what's B? B equals m squared minus n squared, which is congruent to 1 minus 1, which is 0 mod 3. So 3 divides B. Since 4 divides A, then 12 divides the product A times B. So that's kind of a cool thing that we didn't know before, right? Anytime you have a Pythagorean triple, because now, of course, if you take any fundamental triple and multiply it by any scale factor, you're still going to maintain divisibility by 12. And so you'd probably never noticed about Pythagorean triples that the two legs always multiply together to give you a multiple of 12. This is just chock full of neat little tidbits about right triangles that, especially if you're ever teaching this in a geometry class or tutoring geometry students or whatever, this is the kind of stuff that at least, you know, your more interested students, the ones who might go into a STEM discipline, who might be inclined to go into math, will get interested in. You know, this is the reason I went into math. I didn't go into math because it was interesting for engineering and stuff. I never have been one for that. I know that's useful. I know the whole world depends on that. But I just went into math because I thought stuff like this was cool. So that's not an aesthetic everybody, even all math people, share, but it is one that, I don't know, I could do this kind of stuff all day, but right now it's nighttime and it's time to go home. I will actually put up some stuff to do with this. I don't know if I'm going to dig back into the stuff that I accidentally did not publish last week, but I'll make sure that doesn't happen this week. And I have thought through an awful lot of these problems. I worked a few more than this. I think I got up through number 16. Of course, we found a few holes in what I did. So anyway, we'll leave that for there. And that's it. Questions, comments?
So cool. I love it.
I just was getting kind of bored, and I thought with some of the other stuff, it's like, okay, there's some neat math here, but it's not necessarily the kind of thing that you'll grab onto and say, oh, I can connect that to a lot of other stuff right away. So, yeah, hopefully this is a good place to go. It used to be better, because it used to have to do with a problem that nobody knew the answer to, and in fact, it wasn't just that nobody had proved it. There was still a possibility it could be undecidable. If you look at the mathematician Kurt Gödel back in the 30s, proved that some propositions in any mathematical framework cannot be proved within that framework. And so there was always still the possibility that nobody would ever come up with a proof because there simply wouldn't be one. Well, now we know that that's not true. So it's not as exotic. Anyway, we'll stop the recording, call that a night, and I'll touch base with the people who are online and see if there's anything we have to do there. But let me first